Hello, welcome. I'm Yuki. Welcome to our second episode of our stream processing. Within this model, we have provided an overview of the process. First, let's talk about input. Input essentially represents an abstract representation of a data stream. There can be various types of input sources, all confronting to an interface. In practice, you can have multiple types of input. We'll define this input based on certain method and attribute we will discuss later. One essential attribute is the offset, which helps track the reading position. Processing involves incrementally queries of input. The processing is triggered periodically. Speaking of which, WL, write-ahead law, is a key concept. Each time processing is triggered, the data and its offset are locked into the WL. Furthermore, the result generated by the query for a batch of data are stored in the result table, serving as an immediate state. Additionally, the output from this result table requires specific strategies, and once outputted, it needs to be logged in a commit log for fault tolerance, like the WL. Now, let's delve into some further considerations regarding this conceptual framework. Let's continue exploring together. Suppose we are performing a 10-minute aggregation operation within a process. How should we go about it? And what problems might we encounter? Let's assume we have a gift here. This is the reason, and below is a timeline. At 12:52.10, we have periodic triggering of the calculation operation. Before 12:05, we receive two data entries. Each entry consists of a timestamp and a string with a word like cats and dogs. Our task is to count the occurrence of each word within 10-minute intervals. So at 12:05, we perform the count, inputting data from 12:02 and 12:03, which fall within the 12 and the 12:10 window. We record the count. For example, cat appears once and dog appears 3 times. By 12:10, we only need to process the new data, as the previous data was already handled by the 12:05 operation. This is an incremental process. After processing by 12:10, we receive data from 12:07, which also falls within the 12 to 12:10 window. In this window, owl appears once and cat appears twice. We updated the state for dog as it appears again at 12:04. By 12:15, we perform another count. However, we encounter a red data point at 12:04, which should have arrived earlier. We need to deal with this delayed arrival. After processing by 12:15, we handle the delayed data from 12:04, and dog now has a total count 4. This is simplified process. You might notice a couple issues. 1. How long should we wait for delayed data? And do we need to process all delays? If you decide to process delayed data, how do we handle it? For example, dog at 12:04. We cannot keep state indefinitely, as that's impractical. Handling delayed data involves some trade-offs. If data arrives within significant delay, it might no longer be useful to process. Thus, two problems arise: handling data delay and managing state. We can't keep state indefinitely to avoid memory exhaustion. The environment poses challenges since stream processing is a persistent task. If our program crashes or the machine fails. We want to continue processing from where we left off at a certain time, not reprocessing everything before that time. Keep this question in mind as we move forward in our discussion. This covers the topic of handling delayed data. We previously mentioned the issue of handling delayed data. So, how should we address this problem? In stream processing, there is a concept called watermark that helps us deal with the delayed data. This watermark can filter out data that arrives later than expected. In other words, if data arrives too late, we can discard it. Additionally, we use watermarks to clean up our immediate state data because we can't keep it indefinitely. So we need something to control this process, and that something is a watermark. For now, you can get a basic understanding of this concept and its process purpose. In the future, I'll explain how watermarks are implemented and how they work. Now, let's move on to the topic of fault tolerance. As mentioned earlier, one of our challenges is how to handle fault tolerance in stream processing. In stream processing, there are several mechanisms for achieving fault tolerance. The first mechanism is related to the stream source. Stream sources are required to have offsets. This means that they can provide data based on offsets, allowing us to continue reading from where we left off after restart. This helps us maintain normal processing states even after a machine restart. The second mechanism involves recording data as we process it. Typically during batch processing, we use write-ahead log, WAL. Save immediately read state, and record commit logs. This set of operations ensures that we can restart our program and continue processing from an offset where it crashed. We can also retrieve and merge our immediate state, ensuring that no data is lost. The third mechanism pertains to the stream sync. It requires that the writes be idempotent, meaning that writing the same data multiple times has the same effect as writing it once. This enables data synchronization and allows for data override, preventing data loss during restart. The specific details of this mechanism will be explored in more depth in the future. For now, it's essential to understand the approaches we use to address fault tolerance. Within this batch processing engine for stream processing, there are certain operations and limitations to be aware of. First, it supports most SQL operations commonly used in batch processing. The majority of supported operations are applicable to batch processing. However, some operations like multiple table joins involving multiple time windows are not supported due to their complexity. Concepts such as limit and offset are not meaningful in the context of streaming because streams are inherently unbounded and limiting or offsetting them doesn't make sense. The distinct operation is also not supported because it's a global operation and streams are unbounded by nature. The order by operation is not supported unless it occurs within an aggregation operation that's synchronized within the aggregation operation and meets certain output criteria. While there are certain limitations, these operations are not commonly used in practical streaming scenarios, so the impact of this limitation is minimal. Streaming processing differs from batch processing in terms of drawing semantics. The course doesn't intend to dive into the details of these differences, and support for complex drawings may be considered in the future if there's a demand. It's important to know that the course won't go into deep details regarding these specific limitations, as they fall outside the scope of the current curriculum. Now, let's dive into the processing flow using an example. First, we'll talk about aggregation operations without watermarks, which are similar to batch processing operations. We won't go into details about these operations for now, but they may involve some immediate calculations. Instead, we'll focus on event type in streaming processing. Now, let's dive into type-based windowed aggregation operations. Windowed aggregation is a typical and widely used scenario in stream processing. We will use scenario to explain the concept. Windowed aggregation operations in streaming are quite similar to those in batch processing. They involve maintaining an aggregation state for records associated with each time window. In this example, we continuously read records from a socket, and each record contains a timestamp and a word. We use a 10-minute window to count the occurrence of each word. The window slides every 5 minutes, creating a sliding window. The triggering interval for our batch processing is set at 5 minutes. Let's take a look at the diagram below, which resembles the one we discussed earlier. Now let's dive a bit deeper. The input stream is the same as what we saw before. The triggering period are at 12:05, 12:18, and 20:15. In this case, we will focus on how the embedded state changes after each batch processing cycle. After the first cycle at 12:05, the records from 12:02 and 12:03 are within the window of 12 to 12:10. The word cat has a count of 1, and the dog remains the same. When the next cycle happens at 12:10, the word owl appears in a different record. The window 12:05 and 12 to 12:15 is a new window, and the count are updated accordingly. At 12:15, the records from 12:04 are processed. Since that is a delayed record, it also falls into the window 12:05 to 12:15, thus the count are updated. This example illustrated how a sliding window aggregation works on a stream. However, it doesn't cover aspects like data latency, state eviction, and output mechanism, which we will explore later. Now, let's extend this example to input delayed records. In this scenario, a record within a timestamp of 10:4 delay arrives after 12:10. It's considered a delayed record and needs to be processed. This detailed explanation of the diagram helps us understand the flow of processing even better. This chart right now, because of this chart, it might seem a little complex. Let's start by examining this each point and the line inside it. What does it represent? First, take a look at the horizontal and vertical axes. The vertical axis represents our timeline. The vertical axis represents the event timeline for this data. The time associated with the data itself. For example, the time when the data was generated. Like this data here, this yellow point. Well, this yellow point represents normal data. It means there's no delay. Now, this red point represents data with some delay, but it's not significant. However, it's still within the data acceptance range. This blue line is the maximum event time. is the length of time, the maximum test time. This maximum event time will be used later when we calculate the watermark. Though we haven't discussed that yet, when we calculate the watermark, we will use this maximum event time. It will continue to be important, so we will emphasize it here. But this red line is the watermark. This red line represents the watermark. Now, let's dive into the detail of this chart. If you can understand this chart, you will get a cleaner picture of the entire stream processing workflow. Of course, there might be still some confusion. This chart took me a while to grasp initially as well. Of course, some parts might still be unclear, because when I first looked at this chart, it also took me a while. Okay, let's move on. Now, let's take a look at the trigger cycle. Does it trigger once every 5 minutes, or how often? Is it triggered once every 5 minutes? For instance, before 12:05, there was no data to retrieve, so the immediate state table was empty. But at 12:10, you can see that just before that, we received 2 data points. One at 12:07 labeled DPG, and another around 12:08 labeled CAD. So our immediate state table now looks like this. We have RO and G1 corresponding to the time window from 12:05 to 12:15. We have 10-minute window that slide every 5 minutes. So this 2 data point falls into 2 different windows. You can see this blue line here. This blue line represents the current batch's maximum event time, which is important for watermark calculation. Although we'll discuss that later. It shows the maximum event time in the raw data we have processed. This maximum event time is crucial for calculating the watermark. But we haven't reached that part yet. So let's continue. Moving on to, we received 2 more data points. One is at 12:04 labeled DAR, and the other is 12:09 labeled CAD. You can see that is 12:04 is marked in yellow, indicating no delay, while 12:09 is marked in red, suggesting some delay. So 12:09 data point represents its survival time, but it arrives after 12:10. So it has a delay, but we will still process it. Why? Because as of 36:03, it falls within the accepted window for watermark calculation, which we will explain later. After processing the data, we need to update the intermediate state table. You can see blue and gray bars here, where blue represents updated data and gray represents unchanged data. At 37:09, we update the CAD entry because as the nice CAD record from the window has been processed. You will notice that we no longer update the CAD entry because the 12:09 data falls within the time window from 12:05 to 12:15. Similarly, by 37:41, the DAR data is updated at 12:14. Finally, at 38:04, we calculate the maximum event time. In this case, it's 12:14 because the previous batch processed data within that timestamp. This is used in watermark calculation. Speaking of watermark calculation, we calculate it by subtracting the maximum acceptance delay, for example, 10 minutes, from the maximum event time. This defines the timestamp until which we can accept data in the next batch. For example, if our maximum acceptance delay is 10 minutes, the next batch can accept data generated after 12:04. Data generated before 1204 will be discarded. To summarize, at 3846, we discard the 1204 data because it had too much delay, and may only consider the 1217 data. This is reflected in the updated state at 3855. I hope this helps clarify the graph. If you still have questions or if I miss explaining something, please feel free to ask. Understanding this graph is key to grasping the stream processing flow. Alright, if you haven't understood it, you can ask questions in the chat. If it's clear, I feel like I've covered about half of it. We might have to cover the remaining half in the next session or the one after that. Because there's quite a bit left to cover, and our time might not be sufficient now. Actually, let me go ahead and finish up the remaining part first. After everyone has seen the processing flow of this program, let's take a look at the various types of windows it actually supports. Let me quickly explain here. One is tumbling window. Then there's a sliding window. There are also session windows, tumbling windows, and sliding windows. Actually, these are quite easy to understand. Let's start with a tumbling window. So, a tumbling window is one without overlap. You can see these are time windows, for instance, from 12 to 1205, then from 1210 to 1215. This is a 5-minute rolling window. Now, a sliding window is different. A sliding window can overlap. Just take a look at this window. You can see that this window overlaps. So here, in this graph, we have a window of size 10 minutes. And it slides every 5 minutes. For example, this is a sliding window. Then there's a session window. A session window has a parameter here. In this case, the maximum gap time is 5 minutes. For example, if we look at the time from the arrival of the last data point until now, if there is no data arriving within 5 minutes, then this window will close. For example, in this window, W1, you can see that at 12:09, the last record arrived. 5 minutes later, that is at 12:14, no data has arrived. So this window is closed. This is a session window. In addition to this, we just mentioned, in addition to these 3 types of windows, there's also the state window. The state window is used in stream processing and also in time series scenarios. It's quite common in this context. Of course, we'll extend experiments in CnosDB. But I won't go into that specific here today. Now let's move on to each type of window. Its definition, characteristic, and implementation. As we mentioned earlier, we give a rough overview of what the window is like. So we won't go into the details here. Thank you everyone. As you all know that our CnosDB Cloud beta is alive now. Welcome to join our Discord channel below, and you can explore more. I'll see you. Bye bye.